This lesson will focus on forces and Newton's laws of motion, and when the session's over, you can find this very document on the website, and there's a link to it in the video description below. So, forces and Newton's laws of motion are one of the most important things to understand for physics, and we're going to start with forces. Basically, anytime an object is in motion, a force must have acted on it. And that's kind of an intuitive thing, and it makes sense. If a ball is moving, someone had to cause that motion. And there are different types of forces, and we'll go over the different types in this packet. And then in the end, we're going to get to Newton's laws of motion, which are his 3 laws that are extremely important to understand the most fundamentals of physics. So, as you can see with these 2 pictures, there are 2 different kinds of forces. One's a contact force and one's a non-contact force. Forces are vectors, which means that they have both directionality and magnitude. I can't say that I kicked a ball and expect you to know everything that there is to know about the situation. I would have to say I kicked the ball sideways, up, down. It needs both pieces of information. And you don't necessarily have to have contact between the 2 objects. For example, if you think about gravity or about electricity or magnets, they don't necessarily contact each other physically. And so on the left side here, you have a table putting a force on a box, and that's via contact. And then here you have 2 magnets attracting each other, and there's no physical object between them causing this kind of attraction. And one other important thing to keep in mind is net forces. Net force is when you add all the forces acting on an object, and you can describe the object being acted on by that one force. For example, if I had a box and I had a person standing on this side and another person standing on this side, and this person is strong and this person is weak, and they start pushing on the boxes. This person pushes as hard as they can, and this person pushes as hard as they can. As you can see, this person is going to be putting a lot more force on the box than this person. And so, as you can imagine, what this results in is the box moving to the left. And if I just took this and subtracted this from it, I would get a shorter line. So it's almost as if there is just one force acting on it to the left. So this is a net force. These are all the individual forces which lead to a net force. Just keep this in mind as we go over the problems in the future videos. Now we're going to go over the types of forces. The most common one that you're going to see on your tests or your practice problems in your book is weight. Weight is basically the force on an object due to gravity. And as I said before, it's a non-contact force. It's always going to be directed downwards for the scope of this course. But when we get to Physics 2, you're going to see that objects outside of Earth, if they're located below the Earth, they're going to be pulled upwards. But we don't have to worry about that right now. And so it's denoted with a W and an arrow at the top. Then the arrow tells you that it's a vector. Then we have spring forces. Spring forces are really helpful to teach physics because they actually have both kinds, push and pull, within one object. And so in this case, you see a box that's attached to a spring that's being released from the compressed state and being let go. And as you can imagine, it's going to be pushed to the right Then when it reaches the end of its oscillation, it's going to be pulled back to the left. And the magnitude is going to be changing throughout. We're going to be talking about that later too. For right now, just keep in mind that a spring can produce a force in both directions. Another one that we're going to see a lot of is the force of tension. Tension, as you might already intuitively know, it's the force that's within a piece of rope or some sort of elastic object that can be pulled, and they can pull an object. Two things to note about the force of tension. The first one is that when you're pulling on an object with a rope, the rope puts a force on the object in the direction that the rope is being pulled in. So in this case, the rope is being pulled to the right, and it puts a force to the right on the object from the force of tension within the rope. That's number one. Number two, when the person who's pulling the rope or the object that's pulling the rope, they are also going to be experiencing the same exact force of tension on that side, which makes sense. If you were to start pulling an object, a box on the ground, you would be feeling tension on your end of the rope as much as tension on the opposite side of the rope. The next force is a normal force. This is really important to understand in terms of terminology, because a lot of textbooks, a lot of questions are going to ask you what is the normal force on a certain object, and it's always going to be the force that's perpendicular to the object. For example, in this case, the wooden table is putting a normal force on the box, and it's always going to be in the direction perpendicular to the object. In this case, it's vertical. However, if I had a box sitting on a table like this, then the normal force would be in this direction, not in this direction. And then we have the force of friction. Friction can work both on an object that's in motion and on a stationary object, and we'll go over examples of those two. The main difference between force of friction and normal force, if you pay attention, is the directionality of the force. A normal force is perpendicular to the object. Force of friction is parallel to the object, which makes sense when you're pushing an object against another object like this. For example, in this case, the paper is putting a frictional force on the pencil, and vice versa. So for kinetic friction, that's when an object is moving. For example, in this case, the object is moving to the right, and the wood is what's trying to keep it from moving. So it's applying a force on it in the opposite direction, this way. And that's why it's hard to continue pushing objects on surfaces that have a lot of friction. And then we have static friction. As the name might suggest, this is the force that acts on an object when it's stationary. For example, if I have a box that's sitting on a tilted table, and if the box isn't moving, something has to be keeping it there, because gravity wants to constantly pull this box down. So a force has to be counteracting it, and it would be the force of static friction. And we're going to be going into more details about static and kinetic friction later on. And then electricity and magnetism. Those are two forces that are non-contact forces. They're beyond the scope of this course. We're going to go over them in Physics 2 in a lot of detail. And one last thing to remember about forces that's extremely important. When you're noting them on your tests or your book questions or any kind of practice that you're doing, a vector always has an arrow on top of it. For example, the force of anything, that you want to call it, it has to have this arrow at the top to show you that it's a vector. Always keep that in mind. So just to practice what we just learned, if I'm explaining a situation where a block is hanging from a ceiling by a rope, what two forces would be felt by the box? So as I said, gravity always will be functioning, and it's always going to be exerting forces on objects. So gravity will be pulling it down, and then the object is hanging from a rope. When I see the word rope, it automatically triggers tension. When the wording says that it's hanging, meaning that it's not in motion, so that means that the two forces are actually equal. And that's what you see in the picture here. And then this leads us to free body diagrams. So a free body diagram is the convention that you use in physics to show all the forces acting on an object, how fast it's going, how slow it's going, what directions the forces are acting on it. And there's some guidelines to always remember. One of the best things to do is to simplify, because it can be really hard to keep up with all the forces acting on an object. At this point, you might not think that there's too much going on, but we're going to be doing some problems where it's a lot easier to simplify. To simplify means to pretend like the object is located at one point, at one dot. And you should always put a dot at the center of mass of the object. And then you want to go ahead and identify all the forces acting on it. So in the case up here, it would be tension and weight. And then for each one, you just want to draw a simple arrow, and this is an important part of it. You want it to be proportionate to the magnitude of the force. So if force 1 is 5 and force 2 is 10, you want the line for force 2 to be twice as long as force 1. And then, just like we said, these two are what make up a vector: directionality and magnitude. 4 is directionality. You want to make sure that if weight and tension are acting on it, in this case, for example, the tension points up and weight points down, because if both point in the same direction, then that means that that object has a lot of forces acting on it in that direction. And the center of mass is where each arrow should originate from. And in the end, you want to make sure that all the forces are labeled correctly. And just to be clear, this is not a correct free body diagram. This is what a correct free body diagram looks like. We have the dot at the center, which represents the center of mass of the object. We have the rope in the black, and then the orange arrow behind it shows the force of tension, and then we have the weight pulling down on it. Very simple, because it's not moving, the same exact magnitude, and this will give you 100% credit on a test. Lastly, we want to go over Newton's laws of motion. These three are extremely important. We're going to start with his first law. Basically, it's saying that any object that is in motion would rather stay in motion. Any object that's at rest would like to stay at rest. And you can think about this. For example, think about sitting in a car that's not moving with a cup of coffee. As the car starts moving forward, the coffee is going to start spilling on you from behind the mug. That's because initially when the coffee is sitting still, it's fine the way it is. And when the car starts moving forward, the coffee is going to try to still stay in that position. But by staying in that position, the mug is moving forward, the liquid isn't. So that means that all the liquid is going to come up like this and it's going to spill on you. And you can think about this in a lot of different scenarios, and you'll be able to grasp this a lot easier. And then Newton's second law. I would say this is the most important law to know for Physics 1, because this formula, force equals mass times acceleration, is used a lot. And you're going to be seeing it in almost every single problem that you do. What this formula does is it just clarifies the relationship between force, mass, and acceleration. Force is the product of the multiplication of the object's acceleration, A, and the object's mass, M. And as you can see, if you want to apply the same force on an object, but you want to have a mass that's a little bit bigger, your acceleration is going to have to be lower. And this, if you play around with this relationship, you can see exactly what's going on. If you have two objects with the same acceleration and different masses, then your force is going to be different. But if you have two objects, for example, and they have the same masses, and you would like to put on one, you want to have a smaller acceleration, that is going to mean that your force is going to be lower. If your acceleration wants to be higher, your force is going to be higher. And another important thing to note about this formula, this equation, is that it represents the net force, what we spoke about at the beginning of the video. Firstly, the mass has to always be in kilograms. Acceleration always has to be in meters per second squared. And basically, every time you do this equation, you do this formula, your force is going to be the net force. Meaning, if I had the same example from the beginning where I had the box, person 1 is pushing on it, person 2 is pushing on it, I would basically take the acceleration of the object, its mass, multiply them, and it would give me the force. The force that it gives me is the force of this minus this. So if this is a force of 5, this is a force of 1, it will give me a force of 4. This, if I was just given the mass and the acceleration of this object, I could find the net force, but there is no way I could tell you that two forces were acting on it and in which direction and what magnitude. We'll see how it's useful to know the net force, because sometimes you're going to have unknowns in your equations, and it's really helpful to see what the net force is to derive the initial forces. And then Newton's third law. Every time an object exerts a force on another object, the second object has to exert the same exact force, but in the opposite direction on the first object. And this is what we call an action-reaction pair. So there's an example here about a coffee mug sitting on a table. And we'll actually go back to an example of that we did at the beginning. We're going to have a box. This time we're just going to have one person. And imagine that you're this person and you push on the box. You would be feeling the same exact force on your hands. And that's what Newton's third law is. Object 1 puts a force on object 2. We'll call the magnitude of it 5 newtons. That means that 2 is putting in force on object 1 for also 5 newtons. And as we described above, newtons, since we had force equals mass times acceleration, the unit of force is newtons, the unit of mass was kilograms, and the unit of acceleration was meters per second squared. So newtons Newton actually equals kilogram meters per second squared. And that's all that we're going to be going over for this lesson. I will post this PDF as well as a series of practice questions on the website that you guys can download and do. And then I'm going to be posting a video going over the questions and the answers in the next video.